Okay, welcome back. This is the video lecture for Chapter 4, Section 6, Relative Motion in One Dimension. So I strongly recommend that you read that section in your book. I'm going to summarize now some of the key ideas, and then we'll also talk about this in class. So the key idea is what we call relative motion in one dimension. Here's the point. If you want to measure important properties in kinematics, two of them are position and velocity for a particle. What you get for the position or the velocity of a particle depends on what is called the reference frame that has been used for the measurement. So first, let's be clear in physics what we mean by reference frame. What we mean in physics by a reference frame is a set of three coordinate axes, all perpendicular to each other, usually labeled x, y, and z, that extend off in each direction as far as needed, and a clock for measuring time. So with the x, y, and z axes, we can measure position, x, y, and z, and with the clock, we can measure time. That set of axes and the clock constitutes a reference frame for making measurements. Okay, in this section, we're going to limit ourselves to just one-dimensional motion. So we're only going to need one axis. We'll probably call it x. And we have a particle, maybe something like this piece of chalk. And this particle, we can measure its position at a given time once we pick a reference frame. Now, the assumption for everything we've been doing so far is that the reference frame we're talking about, maybe this ruler, could be part of a reference frame, right? It could be part of our x-axis with a chosen origin at one end. The assumption has been that our reference frame is fixed to the ground, isn't moving relative to the ground. The reference frame is not moving relative to ground, Earth, and our particle, of course, could be moving relative to our reference frame. And at any given time, we record the x value, and that's its position. But one of the things you learn in physics is that you're not limited to one reference frame. And that's actually a pretty important idea in physics. We'll come back to that in this class and in later physics classes. But let's imagine that we had a reference frame that was not fixed to the ground, but was riding along parallel to the ground, maybe on a cart on wheels that's just rolling at a constant rate in a straight line. Okay? And so this now could represent the reference frame, the ruler, the x-axis, on this moving cart that's moving relative to the ground. That's a perfectly valid reference frame for making measurements from. Now we're still observing our particle, i.e. this piece of chalk. But now we would be observing it from the moving reference frame. Okay? And what we get for position and velocity of our particle can be different if we measure them from different reference frames. And that's what this key idea is saying. Position and velocity of a particle depend on the reference frame used for measurement. This idea, kind of straightforward enough to say, can still get rather confusing. So let me show you a YouTube video next. Let me go over to it. And I'm going to first set up what we're going to see in this YouTube video. But the point behind it is that velocity, one of the important quantities in kinematics, is a relative quantity. The value you get for velocity depends on the reference frame you measure it from. Here's what's going to happen in this video. The videographer is at rest in a reference frame on a train, old-fashioned train. Okay? And is recording the video from this reference frame on this train. You're looking out the window of the train. First, let's just watch it, and let's see if you can detect what the motion is. Okay? Because I will tell you, there is another train in this video. So we're sitting in one train, looking out a window, and we see another train. And let's just try to keep track of what's moving relative to what. Okay? Get this going. Okay, now, what did we observe there? It can be tricky, so I'll tell you what was happening. At the beginning of the video, the reference frame that we were in, we're the videographer, was on the train that was moving relative to the ground. And the train initially that we saw out our window was not moving relative to the ground. But during the course of the video, the roles reversed. And the train that we were on, from the video's perspective, stopped moving relative to the ground, and the train we saw out our window started moving relative to the ground. So by the time the video ended, the roles had been exactly reversed. It's not immediately obvious when you watch that that's what's happening. Motion is relative, okay, not absolute. And it can be a little bit tricky to ascertain from just visual cues, like in a video, what's moving relative to what. So I want to try to set up a structure here where we can analyze the motion of an object from either one reference frame or another and compare those measurements. But we got to set up a structure here that we can apply very systematically and very carefully. Otherwise, we'll get hopelessly confused. Okay? So here's the kind of scenario we're going to talk about. We're going to limit ourselves to one-dimensional motion here. The picture I have now in the middle of this slide is very important. Let's make sure we understand. Because what we have in this picture is one particle. There it is. It's labeled P. One thing, one particle being observed, and two reference frames from which the particle can be observed. There's reference frame A, and there's reference frame B. And neither reference frame is more important than the other, has priority over the other. Either one is perfectly valid reference frame with its own x-axis and origin and all that for making position measurements. Okay, now, the picture that's drawn here, well, the implication, I should say, is that the frames are moving relative to each other. Frames A and B are moving relative to each other. The picture is assuming that we, the observer, are at rest in frame A. Maybe here we are standing at the origin in frame A, and we're watching. Okay, we're watching what's going on from the origin of frame A. And we see two things. We see the particle P, and we see frame B, both of which can be moving relative to us in frame A. Okay? All right. So our job then is to record the position of the particle for us in frame A. Let's just do that first. That's not that hard. We have an x-axis for frame A. It's going right down there. You can just see it. Right along there. It's labeled X. It's the x-axis for frame A. And right here, I'll try to emphasize it so that you can see it clearly, is a tick mark that denotes the x-coordinate of the particle in frame A. Right there, it's X, and here's how we're going to denote it. We're going to put two subscripts, P, A. And that's very important. Two subscripts, and the order is important. The first subscript is the thing that is being observed. Thing being observed. In this case, it's the particle. The second subscript is the reference frame that you're observing the particle from. So the reference frame for the observation. And that's going to be very important in this section of Chapter 4 that we use this subscript notation and we use it consistently and carefully. So what I'm referring to right now is that tick mark right there. It's the x-coordinate of particle P as observed by somebody in frame A. All right. Now, what if our observer was in frame B? Let's bring on another observer. Now we have an observer here at the origin of frame B, looking out onto the world to see what they can see. And of course, they see particle P. And they have their own x-axis in frame B, and there's the tick mark on the x-axis for frame B that denotes the location of the particle P. Oops, pardon me, I'll get rid of some stuff. And how are we going to denote that x value? It's going to be x sub pb, the x-coordinate of particle P as observed in frame B. And now what I want to do is I want to compare those two x measurements. What does observer in frame A measure for the x-coordinate of the particle? What does the observer in frame B measure for the x-coordinate of the same particle? And how do we compare those two x measurements? All right, if we look carefully at this picture, it's going to tell us how. Okay, let me try to show you, hopefully without erasing too much stuff, what we want. This right here is the x-coordinate of the particle as observed in frame A. You go from the origin of A out to the tick mark on the A-axis, that is the location of the particle. This right here, that double-headed arrow, represents the x for the particle in frame B. Goes from the origin of B out to where the particle is. Now let me add one more distance right there. That's the distance between the origins of the two frames. We're going to denote that distance as x BA. What does that mean? It's the x-coordinate of the origin of frame B as observed from frame A. Because in frame A, you can observe frame B as well as the particle. Now, if that's the case, notice something. This distance right here, xPA, is equal to this distance right here, xPB, plus this distance, xBA. And that's all. That's the main observation you have to get. And here it is written right down here. But it's very important. I'm going to put a star by it. It's going to be our relative motion relationship. And it tells us how to relate the x-coordinate of the particle in frame A to the x-coordinate of the particle in frame B. And the relationship goes like this. The x-coordinate of our particle, as observed in frame A, is equal to the x-coordinate of the particle as observed in frame B plus the x-coordinate of frame B as observed in frame A. And that's just the fact that I said just a minute ago. This long distance here, xPA, is equal to this shorter distance here, xPB, plus that distance there, xBA. And that's exactly what this says in symbols. xPA equals xPB plus xBA. And that is the key equation relating positions in one particle, but observed from two different reference frames, right? There's one particle being observed and two reference frames for observing it. Now here's something I like to point out when using the relative motion relationship. There's a pattern to these subscripts, and that's why it's really important that we stick to this proper use of these subscripts, because if you use the subscripts properly, then you can figure out this pattern I'm going to show you. This is how you can always check if you're putting down the quantities in the right order. In the xPA equals xPB plus xBA equation, the first subscript on the left, the particle, the thing being observed, has got to be the same as the first subscript on the right, the particle being observed. The last subscript on the left, the reference frame A, has got to be the same as the last subscript on the right, the reference frame A. And the middle subscripts on the right, there and there, must be the other frame B. So if your subscripts adhere to this pattern, then you know you're combining those quantities correctly. Okay? You know you have the equation correct. If it doesn't follow this pattern, it's not correct. Remember, this equation just came from my picture right up above. That's how I know it's right, because it's a very simple picture. Okay, now, let's go on. The formula I've marked with the red star tells us how to relate position of particle in A to the position of the same particle as observed in B. Sometimes I might want to know how to relate velocities. What if I measure the velocity of the particle in A and the velocity of the particle in B? How are they related? I showed you the video where there was relative velocity. All you do is take equation star and take the time derivative of both sides of every term. Okay? And then you can relate the velocities of the particles as observed in the two reference frames, A and B. And it's the same as equation star, except instead of x's, you have v's, because you're talking about velocities. So I'm going to put another star here, because this equation is just as important as the first one. And it's relating velocities. The velocity of our particle, as observed in frame A, is equal to the velocity of the particle as observed in B, plus the velocity of B as observed from A. And that's how you can relate velocities of a particle observed from two different frames. Now, we went from a relative position equation, taking a time derivative, we got a relative velocity equation. How about we go for acceleration now? All we got to do is take the time derivative of both sides of the second star equation to relate the acceleration of the particle, p, observed from the two frames A and B. And here something interesting happens that's different. First of all, in this chapter, we're going to assume that the velocity of the frames relative to each other is constant. Okay? The velocity of frame B as observed in frame A is not changing. If that's true, when I take the time derivative of the second star equation, when I take the derivative of the VBA, I'm taking the derivative of a constant. That gives me 0. So all that happens then is I have that the acceleration of the particle in frame A, which comes from differentiating with respect to time that v, is equal to the acceleration of the particle as observed in frame B. That comes from differentiating that v. So as long as the frames are moving at a constant velocity relative to each other, the two observers, the one in frame A and the other in frame B, will agree on the particle's acceleration. And that's important to remember. The two observers, one observer in frame A, the other observer in frame B, both observing the same particle, will not necessarily agree about the position of the particle or the velocity of the particle, but they will agree about the acceleration. And it's not that one observer is right and the other is wrong. Both observers are correct for their reference frame. Okay? Now, the last thing I want to show you is a couple of animations from Wiley Plus that show you a relative motion with our reference frame structure, as opposed to like a real-world video with locomotives, just for the reference frame structure. And what's happening here is you got the particle P, that's being observed, okay? And you're going to have two reference frames, A and B. And it just so happens at time 0, the two reference frames overlap. But when we run the animation, we're going to see that, first of all, we're observing from frame A. So you can imagine that you're standing at rest at the origin of frame A. And you're watching two things, particle P and reference frame B. So I'm going to run this animation for the given settings, and I want us to talk about what we see. It's not going to be that dramatic, but it's good for us to practice. So here we go. Okay, it ran for 8 seconds. I'm going to set it back again. I want you to focus on the particle P. Watch the particle. We are observing from frame A, and we are observing the particle. What can you tell me about the position and the velocity of the particle as observed in frame A? If you want to pause the video and think about it a little bit, feel free to do so. Okay, did you think about it a little bit? What do you observe about the position and the velocity of particle P as observed in frame A? Did you say the position isn't changing? Because there's particle P. Did you see it move? It's always at 20 on this x-axis, isn't it? The x position of the particle as observed in frame A is constant. So what does that mean the velocity of the particle as observed in frame A is? It's 0. That's a perfectly valid assumption, observation for frame A. I'm going to reset. Now I want you to watch what frame B is doing. Again, we're the observer in frame A. What is frame B doing? It's just moving along, right? It's represented by those purple axes, Y, and then there was an X. And as we observe it in frame A, frame B is just moving to the right. So if we study the origin of frame B, well, it starts out at the same origin as A, but it's moving to the right. And after 8 seconds, it's a little past 30 meters from the origin of A. So frame B is moving to the right. So it's got a velocity. In fact, its velocity is 4 meters per second, which you might be able to see on that slider there. So we have observed two things from frame A in this animation. Particle P and frame B. All right, now, basically the same situation. Particle P is shown, but now we're going to observe from frame B, the frame B that I just showed you. And I'm not even going to show you frame A. I'm just going to show you frame B and the particle. When I run the animation and observe particle P from frame B, how do you think it's going to move? You want to think about that for a minute? You're welcome to pause the video. Okay, let's think about this. In frame A, we observe particle P to be at rest. And we observe frame B to be moving to the right at a constant rate of 4 meters per second. But now we're going to observe the particle from frame B. I don't think the particle is going to be at rest in frame B. In fact, it's going to be moving to the left at 4 meters per second. Let's watch. For 8 seconds. Okay? It went 32 meters to the left in the negative direction. So that's what you would observe for the particle P in frame B. It's not at rest. The particle P is at rest when observed in frame A. It's not at rest when observed in frame B. Motion is relative. What you observe for the motion depends on the reference frame that you observe from. Okay? But again, the main takeaway points that I want you to remember here are the starred equations. They tell you how to relate position measurements of the particle in the two frames and velocity measurements in the two frames. So remember those two starred equations and be careful with the subscripts. On all of these quantities, the x or the v's, the first subscript is the thing being observed, and the second subscript is the reference frame you're observing it from. All right, we're going to have some class time where we practice using this idea, but that's all for this video.